In this lesson, keys and couplings. In the previous lesson, we have discussed about the design of flange coupling and one problem also we have solved in that lesson. Now, once again, let us have some more problems, solved problems on unprotected type of flange coupling, as well as small theory related to marine flange coupling. So, flange coupling, solve problems. In the previous class, the design of flange coupling includes, and the main parts are hub, flanges, keys, bolts and nuts. And also we have discussed the previous lesson, design of flange coupling involves calculation of proportions of all the parts, that is hub, flange, keys and bolts, etc., and check for their strength under various under the load conditions, given load conditions, right? So this is the previous discussion we have completed, and also we completed one problem also. In this lesson, on completion of this lesson, you will be able to solve the problems related to the design of flange coupling, which is unprotected type of flange coupling, and also you should have a small concept on, simple concept on marine flange coupling, right? So let us go to the lesson once again. So problem number 1. Previously one problem we have solved, and now today so here the problem is design a flange coupling to connect two shafts in order to transmit. Design a CI flange coupling, cast iron flange coupling, to connect two shafts in order to transmit 7.5 kilowatts power at 720 revolutions per minute. The power is given to you and speed is also given to you. With this data, you can calculate the diameter of the shaft. That means from power formula, P is equal to 2 pi N T by 60. P is there, N is there, only T is not there. And torque you can calculate by using power formula, by substituting power value and the speed value. And the given data is the permissible stresses may be assumed as permissible shear stress 33.33 meters per millimeter square. This permissible shear stress for shaft, bolt and key material. And permissible crushing stress for bolt and key material is 60 Newton per millimeter square. And permissible shear stress for cast iron flanges and hub, that is 15 newtons per millimeter square. See once again, let us see the unprotected type of flange coupling related, and this is small d, which is the diameter of the shaft, and it is the capital D, which is the outer diameter of the hub, whereas inside diameter of the hub is diameter of the shaft itself, and this is the dp, circle diameter 3d, and d2 actually this is do, we can call it as 4d, or the diameter of the flange, and tf is thickness of the flange. This is all about the unprotected type flange coupling. So power is there for us, which is 7.5 into 10 to the power of 3 watts or 1000 watts, and speed is in revolutions per minute 720, and permissible stresses for bolt, key and shaft is Fs, that is 33 Newton per mm square. Permissible crushing stress for bolt and key Fc is equal to 16 newtons per mm square, and permissible shear stress for cast iron, that is for hub as well as the flange, that is Fs1 is equal to 15 newtons per millimeter square. So now let us first of all find the diameter of the shaft by using power formula and torque formula. So, this is the torque formula that is there. T is equal to, that is power formula based on this 60. T is equal to 60 into P by 2 pi L. You will get your torque in Newton meters. 99.522 Newton meters, that is 99,522 Newton millimeters. So with the torque equation, T is equal to Fs into pi dq by 16. With this you will get your shaft diameter. Shaft diameter of substitution of torque Fs, you will get 24.86. 24.86, that is rounded up to nearest 5 value, that is 25 as per the standards, right? Now design of hub. In this design of hub, inside diameter of the hub cap, inside diameter of the hub is nothing but the shaft diameter itself, that is d is equal to 25 mm, and outside diameter of the hub d is equal to 2d, that is 50 mm, and length of the height b is equal to l is equal to 1.5d, that is 37.5 mm. After calculating these proportions, let us check for induced shear stress in the hub itself. That is, T is equal to Fs1 is equal to pi into d power to 4 minus small d power to 4 by 16d. With this Fs, let us induced shear stress should be calculated. That will become 4.327. This value, this induced shear stress in the hub, is less than its permissible value 15 Newton per millimeter square. So the design is safe. As the induced stress is less than permissible value, the design is safe in terms of in case of hub. And now let us have the flanges. Now here in this case, thickness of the flange TF is equal to 0.5D, as it is the unprotected flange coupling. Then we will get thickness of the flange 12.5 mm. And outside diameter DO is equal to 4D, that is 100 mm. And now check for induced shear stress, and T is equal to pi dTF into Fs1 into D by 2. After substituting, let us calculate the induced shear stress. Because D is there for you, that is 2D, that is 50, and TF is there 12.5, and torque is also there for us. Only the unknown value here, induced shear stress, is equal to, after substitution, you will get 2.03 Newton per mm square, which is less than its permissible value. So as the induced shear stress is less than its permissible value, then the design is safe in case of flange coupling. Flanges, design of flanges. And now the design of key. Same as in the previous case, width of the key d by 4, that is 7 mm. With thickness of the key d by 6, it should be d by 6, and 25 by 6 here it is correct, that is 5 mm. So length is equal to, length of the key is nothing but the length of the hub, which is 37.1.5d, that is 37.5. Now check for shear strength in the key. Fs is equal to 2t by WLD, that is T is equal to WL into Fs into T by 2. Fs is equal to 2t WLD, which should be 30.33 Newton per millimeter square, which is less than its permissible value. So as the shear stress induced in the key is less than its permissible value, the design is safe in respect of shear strength. And now first check for crushing strength of the key, that is T is equal to T by 2 into L into Fc into D by 2, and Fc is equal to 4P by TLD. and the T is there for us. T small d is also there. L is equal to there. D is also there. Fc, let us induce pressure stress, let us calculate 84.9 Newton per millimeter square. But whereas it is 16 Newton per millimeter square. Induced stress is greater than its permissible value, and the key may fail in crushing. The key may fail because it is 84.9 whereas it is 61. That's why the design is not safe because of, in case of key. So let us change the dimensions. Change the dimensions of key value. Key. So therefore, adapt key of the following dimensions. Let us take width of the key is equal to 8. Previously it is 7. And thickness of the key is equal to 6. Previously it is 5. And length of the key is 37.5. It is now 48. Let us substitute once again crushing strength of modified key is Fc is equal to 240 into TLD, that is 55.29, which is less than the given permissible value. So like this you have to modify whenever there is a possibility of failure in any of the, either it may be of the flange, or it may be in the hub, or it may be in the key, or it may be in the bolt also. In such cases, you have to change the dimensions and check for the, once again, the stresses. Okay, now after changing the dimensions, you got this value in which crushing strength, which is less than the permissible value. The design is safe. The stress induced are in the permissible limit, therefore the design is safe. Now, in case of design of bolts, as up to 40, it is for shaft up to 40 diameter, it is 3 only. So n is equal to 3 for shaft diameter of 25 mm. And bolt circle diameter or pitch circle diameter dy is equal to 3d, that is 75 mm. And check for crushing, shear strength of the bolts. But whereas there is no value of diameter, nominal diameter, that's why let's calculate by using considering the shear strength formula for the bolts 5 by 4 d1 square into n into fs into dp. dp is also there for us, n is also there for us, d1 is also there for us, whereas fs also permissible value is given for us. That's why d1 let us calculate and check for crushing stress. d1 is equal to 8t pi n fs dp. Thereby the d1 is equal to 5.84, which is to be rounded off to the next higher value 6, or let it be the 10. So bolt diameter is equal to d1 is equal to 6. Now considering the crushing strength of the bolts, P is equal to d1 tf into n into fc into dp by 2, and fc is equal to 2t by b1 into tf into n into dp, that is 11.79. Considering the stress induced is less than, crushing stress induced is less than permissible value. Hence, the bolts are safe against both shearing as well as the crushing. So, like this, you have to calculate your design problems for flange coupling. Okay. So, let us see the marine flange coupling. Small data related to the marine flange coupling. So marine flange coupling, it in ships we are going to use this type of marine applications. And here, whereas the previous case there is no hub, in this case directly the ends of the shafts are made into a projected as flanges. So here you can see this will be the flange which is projected integral with the shaft. That means this project end of the, and corresponding recess is also there and projection is also there, which will help you in perfect alignment, perfect alignment in this. So here we are going to use tapered bolts instead of hexagonal bolts. We are going to use tapered bolts. In this coupling, in this marine flange coupling, flanges are integral with the shaft, number one, and in this tapered bolts are used. And here in this case, design of this coupling includes only determination of shaft sizes, flange dimensions, and bolt sizes, that is tapered bolt sizes. Only these three are there in this, right? So, in case of marine flange coupling, we are not going to apply the number of bolts same as in the previous case, but here in this it is different. In previously it had up to 40 mm, it is 3, up to I think it is 100 mm, it is 4, and up to 8 mm, it is 6. But now it is different as per the IS, according to IS 3653 1966. The number of bolts N for this, that is marine flange coupling, are given as below. Here you can see N is equal to, that means number of tapered bolts is 4 for shafts diameters 35 to 55 mm, 35 to 55 mm, and 6 for the shaft diameters 56 to 150 mm diameter. And it is 8, N is equal to 8 for shaft diameters 151 to 230 mm, and 10 for shaft diameters 231 to 390 mm, and then 12 number for shaft diameters above 390 mm, above. So the numbers are 4, 6, 8, 12, sorry, 10 and 12, right? This is the, as per the standards, IS 3653 1966 number of bolts in case of marine flange coupling are like this. So summary of this lesson, once again let us see. Design of unprotected type flange coupling include the following steps. Once again let us see the steps involved in this. Obtain the torque from the equation power. Obtain torque T from equation power formula, that is P is equal to 2 pi nt by 60. 2 pi nt by 60. And obtain diameter of shafts D from torque formula, that is Fs is equal to pi dq by 16. And then obtain the proportions of hub. Obtain the proportions of the hub D. Outer diameter D is equal to 2D, 2 times of the shaft diameter, and L is equal to 1.5 times the shaft diameter. And check for induced shear stress using the equation, that is T is equal to Fs1, that is shear stress induced in the, sorry, shear stress for hub material into pi d power to the 4 minus small d power to the 4 by 16d, and obtain proportions of flanges. Tf is equal to 0.15 times of the shaft diameter, and also DO, outside diameter of the flanges, is equal to 4d. And check for induced shear stress Check for induced using equation T is equal to pi dTf is equal into Fs1 into d by 2. That is, next is key design of the flange coupling. Obtain proportions of key. Width of the key is equal to d by 4, where shaft 1/4 of the shaft diameter, and the thickness of the key is equal to 1/6 of the shaft diameter, or 2 by 3rd of width of the key, and then length of the key is equal to 1.5d, and check for shear strength of key using the equation T is equal to WL into Fs into d by 2. WL into Fs into d by 2, and check for crushing strength of the key by using the equation T is equal to thickness of the key by 2 into L into Fc into d by 2. With these two equations, the key strength may be uh, verified for the induced stresses and allowable stresses, induced stresses and allowable stresses, right? And now let us, for design of, in case of design of bolts of flange coupling, first of all choose the number of bolts n for the given shaft diameter. That is, previously I told you that is 3, 4, and 6 based on the shaft diameter. And now obtain bolt circle diameter dp is equal to 3 times of the d, 3 times of the shaft diameter, and check for shear strength using the equation. If sometimes they may not give the nominal diameter of the bolt, in such cases by using the shear stress equation, we have to calculate the nominal diameter of the bolts by using this formula. That is, T is equal to pi by 4 d1 square into n into Fs into dp by 2. With this formula, let us calculate whenever they have not given the size of the bolts. In this case, we have to calculate by using this equation d1. You have to calculate, and you have to check for crushing strength using this equation. Crushing strength for using this equation. That is T is equal to torque transmitted is equal to d1 into Tf into n into Fc into dp by 2. Like this, first of all, you have to calculate shaft diameter, and then have to check for hub stresses, and check for flanges strength, and check for key strength, and check for bolt strength. And this is the step-by-step procedure for flange coupling. Now let us have a small quiz over this lesson, today's lesson, and also previous lesson. The outside diameter of flange in flange coupling. The outside diameter of the flanges, outer diameter. The outside diameter of flange in flange coupling is 3D, 3 times of the shaft diameter, 2 times of the shaft diameter, and 4 times of the shaft diameter, and 0.5 times of the shaft diameter. Once again, you can see all these are the proportions of various parts of various diameters of parts. And here you can say 3D is nothing but the proportions for pitch circle diameter or bolt circle diameter. It is for pitch circle diameter or bolt circle diameter. Whereas 2D is the outside diameter of the hub itself. That is capital D is equal to 2D, which is the outside diameter of the hub. Whereas 0.5D is the thickness of the flange for unprotected flange coupling. Thickness of the flange for unprotected type flange coupling. So only the letter is C, that is 4D, which should be the outside diameter of the flange. Generally, you can see D is the shaft diameter, 2D is the outside diameter of the flange hub, and 3D is the pitch circle diameter, and the outside diameter is 4. Simply, you must remember like this. And thickness of the flange is 0.5D for unprotected type flange. Let us see the answer. Let us right. C is the right answer for outside diameter of the flange. The flange coupling is 4 times DO is equal to 4 times the shaft diameter. Next quiz is flange is checked for flange, only the flange, what flange, not flange coupling, it is only flange. Checked for crushing only, shearing only, and crushing as well as shearing only. Any of the above, which is the right answer. Generally, the shearing stress induces at the junction of hub as well as the flange. So there is a possibility of like this shearing. So this may be the hub and this may be the flange, and there is a possibility of shearing at this. As I told you, shearing area is pi capital D into TF. And next is there is a possibility of crushing also sometimes at the bolts and the flange. Bolt and flange, that is pi small d1 into thickness of the flange will be the crushing area. So that may also take place sometimes. Let us see the answer. As per my knowledge, B should be the answer, but let it be maybe C also. So shearing only the flanges, flange in flange coupling is checked for or verified for induced shearing only, induced allowable and induced shearing only. If the allowable shearing is greater than the induced shearing, then the design of flange is safe. The equation for to check the crushing stress of bolts. The equation for to check the crushing stress of bolts. So A is equal to T into T is A. T is equal to D1 TF into N into Fs dP by 2. If you observe this equation, this may be the crushing area for n number of bolts. Then it is Fs is the notation used for shearing only. So that's why A is not right answer. And let us see D. So here is the D1 TF into N into FC into DO. Here DO is there. So this is not for, we are not going to check for outside diameter of the coin, but we are going to for have circle diameter DP. So this is also wrong. And let us have this C, T is equal to D1 into TF into N into FC into dP by 2. So here if you see, and last one is DO, T is equal to DO into TF into N into FC into dP by 2. Here only the D in case of D. So let us see C answer maybe D is equal to D1, it is the bolt circle, the bolt diameter, and TF is the thickness of the flange, and is equal to number of bolts, and FC is equal to crushing stress induced in the bolt, and dP is the fixed circle diameter. Maybe C is the right answer. If you see D also, T is equal to DO. DO is not the diameter of the bolt, it is the outside diameter of the flange. That's why there is no possibility of answer for A because it is DP, FS is there, and B, if it is DO is there, that is also wrong answer, and D is there, only DO is there, that is also wrong answer. So finally the leftover answer is C. In this there is no wrong notations, that is D1 is right, TF is right, N is right, TFC is right, and DP is also right. That's why so C should be the answer for this equation. Check the question says volts. That is so D is the right answer. Right? Answer B. So here another quiz. The diameter of the shaft is 40 mm. The shaft diameter is 40 mm. Small d, and pitch circle diameter is generally dp is equal to, actually we are having 3d, 3 times of the shaft diameter, and it should be 3 into 40, nothing but 120 should be 1 mm. So A is equal to 100 mm. It is anyway is not right. 120 mm may be right. 60 mm is 2D only, so it is wrong. And 4D is also wrong because 10 times of shaft diameter. This is wrong. This is wrong. And after calculation, the circle diameter of the flange coupling, capital DP is equal to 3 times of the shaft diameter. That is 3 into 40. That is should be B. Answer should be. So B is the right answer. So let us have a small assignment. Let us discuss this also. So here in this case, a solid circular shaft is to transmit 1.25 megawatts. That is power transmitted in megawatts. That is speed is 240 mm RPM. It is connected to another shaft with flange coupling, which has 6 volts, where N is equal to 6 volts, equally spaced on a pitch circle having a diameter of 1.5 times that of shaft diameter. So dP is equal to 1.5 D, and the allowable shear stress are 75 newton per mm square for shaft and 109 newtons per mm square for bolts. Determine the diameter of the shaft, diameter of the bolts required in this. So diameter of shaft is easy for us to solve this problem. 1 point power is there for us, and then speed is in there. By using power formula, you can calculate torque, and torque is equal to pi by 16 FSDQ. FS is for shaft is given 75, so that's why we can calculate the shaft diameter D is equal to cubic root of 16T by pi Fs. So with that you can calculate very easily without any difficult. Um, that is shaft diameter. Whereas the diameter of the bolts is here allowable shear stress for bolts is given for us. So that is T is equal to pi by 4 d1 square into N is also there for us. D1 should be calculated. Torque is there for us from the power formula. Into Fs is given to you, and then dP is also given for us 1.5 times 1. That means also there for us, so automatically you can get your bolt diameter, right? I think it is very easy problem for us. So diameter of the shaft is 150 mm, and diameter of the bolt D1 is equal to 31 mm. Let us try yourself. And next problem is, what is the maximum power can be transmitted safely by flange coupling with the 6 bolts? N is equal to 6 of 10 mm diameter. Bolt diameter D1 is given for us 10 mm. In a 75 mm bolt circle, diameter bolt circle, that is dP is equal to 75 mm. When revolving it 1160 rpm. So rpm is also given for us. So use design stress as 25 newton per millimeter square. So we have to calculate power, maximum power that can be transmitted safely by using this formula. That means torque you have to calculate by using uh, shearing stress of the bolt. So T, capital T is equal to pi by 4. D1 is there for us square into FSC. Design stress is there for 25 newtons per meter square. N is there for us, and DP is also there 75 mm. So with this you can calculate torque, and speed is also given for us. Thereby, after calculating the torque value by using the shearing strength of the bolts, and speed is there, torque we can calculate by using both torque as well as speed. Power is equal to 2 pi 80 by 60. So it is also a very simple problem that we can solve this with this, right? So power is equal to 53.67 kilowatts. So next is a cast iron flange coupling connects two shafts to transmit 8 kilowatts at 800 rpm. So torque you can calculate with this given data, and the permissible stresses as follows: shear stress for shaft in voltmeter 30 Newton per mm square, and crushing stress for bolt material is 60 Newton per mm square, and permissible shear stress for cast iron is also there for us. So design only hub dimensions, flange dimensions, bolt dimensions, and number of bolts. So with this you can calculate hub dimensions also. With this formula you are going to get torque value, and with this shear stress value you can calculate after getting torque. Shaft diameter you can calculate by using shaft diameter. Hub dimensions cannot be calculated. And thickness of the flange also should be can be calculated. And you can check for flange also, and diameter of the bolts we can also calculate, and number of bolts based on the shaft diameter also we can keep. So like this we can calculate this problem also without any difficult for us. So diameter of the outside diameter of the hub is given for us 60 mm. That means maybe shaft diameter 30 mm, and L is equal to given for us 45 mm. Thickness of the flange 15 mm. DP is equal to 90 mm. Right? DO and also N is equal to also there for us, and bolt size is also 6 cm. So friends, let us conclude this session for today. And in this lesson we have discussed about one problem on unprotected flange coupling design, and small related theory of marine flange coupling, and one in summary case step-by-step procedure for design of flange coupling, and some quiz questions, and also some assignment questions also I have discussed so far. So let us conclude this session.